visualization application project that I worked on. And I alluded to this earlier when I talked about. I worked with a team that was interested in doing blood flow visualization. And so the project is really about coupling two different simulation models into one thing, where basically they have two. Well, first, to set up the problem, they're interested in looking at blood flow in the brain, and in particular, they have a data set that they. So what you see here on the left is the arterial tree from the brain, and this is reconstructed from MRI data from a real patient, and that patient has an aneurysm, and so they're interested in how the overall blood flow patterns in the arteries affect small-scale particle events inside the aneurysm. So they're interested in how these two features of the two different, largely different scale events affect each other. And so they have two different codes that simulate them. So they have a finite element code that runs and calculates the overall flow, and then they couple that with a molecular dynamics code that does particle dynamics of individual particles, and they're looking at how they're aggregating on the wall of this aneurysm, forming a clot, and they want to understand how the formation of this clot could cause that aneurysm to burst. Right, so they're coupling these two different codes together, and what they were interested in doing is, so we talked earlier about how the format of the data when you're doing the simulation is generally very different from the format of the data when you're doing the visualization. So they already had some utilities that they used for post-processing, where they'd save the data out in their native format. They would read it back in, do some transformation on it, and basically turn it into VTK, and then spit that data back out. And then they'd move down the pipeline, read that reformatted VTK data back in, and do their visualization. So one of the things that I did was I worked with them to incorporate that data transformation as a reader plugin for ParaView. So now instead of doing this multi-process post-processing step, they generate their data as they did previously, but now we have a reader for ParaView that will read in their native data format, do this transformation to VTK, and then push it directly into ParaView on the fly. So I'll talk a little bit about the simulation itself. It's a simulation code called NekTar. Again, it's a spectral element code where they have non-overlapping elements, and the way they have this multi-patch approach where they decompose the overall domain into multiple patches. So if we go back to here, you can see how over here on the left, each of these colored regions is a different patch, so that each of those is essentially a different MPI job that communicates with each other. So they have the communication that happens essentially within one of these regions. They sort of isolate it to this patch, and they do communication and do some coupling at the boundaries of those subdomains. And so then they save off their data where basically the mesh of that data is saved separate from the solution data. And so when we talk about a little bit later about how when we integrate this with the ParaView reader, we can read in the mesh data once because that's not changing over the course of the simulation, and then just read in the new data for each time step and not have to reread the mesh. So here's how we coupled it. So basically, as we mentioned, ParaView has this reader plugin modularity. So we're coupling we wrote a reader plugin that reads the data in its native format, calls out and uses NekTar, its own libraries, and its routines for doing the reading. And then the other thing that we were able to do with it was use it for doing additional computation as well. So they already have methods for doing different derived quantities that they're interested in looking at, in addition to the data that they're already saving to disk. We're able to incorporate those routines and access them access the NekTar routines from within ParaView. So it uses NekTar for the I/O and the computation, and then leverages all the utility of ParaView for doing the rendering, and all the other visualization routines like generating streamlines, doing glyphs, all that stuff. This is actually an old slide. There's a lot more capabilities involved with it, but basically, so through the GUI, you're able to select which variables you want to load. And another important thing is being able to interactively set the data resolution. Each of the elements of their, they have this, the finite elements that they're calculating, and then when they load it into ParaView, they can resample those elements, change the resolution up or down, so that and use NekTar's routines for doing the interpolation. And again, I mentioned that for time-varying data, it only needs to read the mesh once at the beginning, and then reads only the new data each time. And we added some stuff for doing data caching. So for over a time series, when you read in multiple steps, when you go back, it caches data, so you don't need to reread the data every time. So here's an example. I don't know how easy it is to see, but so changing the resolution from the lowest resolution, and it's hard to see in these two images, but it's in the lower resolution one, it's more faceted, and then in a higher resolution, obviously it's more smooth, more accurate results. And that's actually another thing when I mentioned doing the derived quantities. Because they're using the finite element code, they're able to calculate it with higher order spectral accuracy. So these two images show calculation of vorticity. The one on the left, it uses ParaView has the capability for calculating it, but it uses the values of the values are already projected onto a grid, and so they don't have the high spectral accuracy that the native code does, because it has accuracy to or access to the data in its native format. So we're able to do those calculations on the spectral elements and then project it over. So these two images were actually done on the same resolution mesh. So there's not additional data on the right. It just had access to the spectral elements again, and we're able to calculate a more accurate result. Another derived quantity was the wall shear stress. That we're able to use their code to extract the boundary mesh and calculate the wall shear stress, which is indicated by the vectors there on the surface of the mesh. And then more recently, the work I've been doing with them, the initial implementation, the mesh was static, and more recently, we've been looking at doing dynamic mesh. So the fluid structure interaction, so the fluid influences the structure, so the mesh changes over time. And the way we implemented that was that the topology of the mesh stays the same. Like we talked about earlier, the connectivity is all the same, but only the vertices of the coordinates of the vertices of the mesh are changing. Instead of recalculating the connectivity every time, we save essentially the displacement of each of the vertices as a variable associated with each of those points, and we're able to apply that to the vertices. So that's probably a little hard to tell the difference, but if we look at both of them together, you can see how the mesh is changing over time. And then this is another example of visualization of the whole thing. And an additional quantity, we're calculating the stress tensor. So these red regions here on those circular sort of regions on the surface are places where there's stress on the boundary of the. Hank spoke about this a little bit earlier too. In addition to having viz as the end product, it's also valuable as a debugging and verification tool. So for instance, I mentioned we're coupling these two codes, the finite element with the molecular dynamics code. And so everything that's going on out here, all this flow, and this is a cutting plane through this aneurysm of the flow data, is generated by one code, and this little subregion here is what's being calculated by the particle dynamics. And so, oops. Right, so this subregion is where this particle dynamics is being run. And so it's important that the boundary between those two areas is accurate. So the region inside this black line here, this is the cutting plane along the boundary where the large area is being calculated by one code and the small region is what's calculated by the other. And so you can see that they match up, right? And so they were using this as a verification tool where they can look at and see that so the red arrows, orange arrows are what's calculated by the finite element code, and then these purple ones are, you can see they're only on they originate on the inside of this space. That's where the particle dynamics is happening. And so you see they're getting the same answers, what they're looking for. And so this was a valuable tool to help verify that. And again, we've also used it as a debugging tool. So this is an example of, this is actually, obviously it's not blood flow. This is a simulation of, it's a dual propeller. You'll see in a second when I step forward. It's two propellers that are rotating in opposite directions. And so they use a NekTar, this finite element code, for doing flow around these propellers. And they were confused because they were running their simulations. They were getting results that they weren't expecting. So they asked me, say, hey, can we use the same visualization stuff that we developed for the blood flow for this propeller stuff and kind of figure out what's going on. And so when I started looking at it, you see the two propellers rotating. Well, in the front propeller, one of the blades is disappearing. And so they had some bug in their code that was not resetting some parameter, doing something wrong, so that as the simulation progressed, the front propeller just disappeared. And so they were able to use by visualizing it, they were able to understand, there was a problem that keyed them into where to look in the code to figure out what went wrong. And so this is a visualization of what they were expecting to see after they fixed the problem, where they're looking at these vortices caused by the flow. This is another example of using, well, this is the same HACC project that Tom spoke about. And so I'm not going to go into too much detail about the science itself, but basically it's this large-scale simulation. And what we were looking at was basically a 10,000 cubed volume of data that we were volume rendering. So we're running on this on a large number of processes. We were trying to understand how to increase our performance. And so one of the things that we did was we were trying to parallelize it. So this is a small chunk. So we're already parallelizing it by running multiple processes, but then we wanted to thread it as well. And we weren't getting quite the performance that we were expecting when we added multiple threads. So I said, well, we thought about, well, what if we color the data not by, each voxel not by the calculated data, but by the thread ID. So by changing the way that we did the threading, we came up with these. So again, so these are sort of colored by thread ID. And so we ran this small problem on 8 threads on each node. And by changing up the way we did some of the data accesses, it changed the way that basically that data was assigned to different threads, and we were seeing different performance based on those characteristics. So just an example of doing visualization as using it as a diagnostics tool, not just for the pretty picture at the end. And this is just another example of that. This is a NEC 5000 data set. It's on the order of like 700,000 elements. And so Visit and ParaView both have methods for, and you saw this earlier too, we're basically coloring the data by process ID. So I'm running this on 64 different processes. And so this is basically, showing how the data is distributed, partitioned among those processes. So this is was a custom reader that I wrote. And so I was playing with, again, sort of different partitioning schemes. And so I wanted to see what the performance of partitioning the data differently among the processes was. And so this was sort of an optimal, each process got a contiguous chunk of elements. And then contrastly, each one got, this was sort of an exercise in sort of illustrating what some of the differences were if you, instead of giving each block a contiguous chunk, you did a round robin assignment of assigning a different, each element to in order to a different process. So the rendering and other performance of looking at these two, the same data set, but partitioned differently, was pretty dramatic. It was much, much slower, maybe not obviously, but for a number of different reasons when it was partitioned in the second way. Again, sort of looking at visualization as a diagnostics and debugging tool, not just for the end result. And at this point, I'm going to turn it over to Venkat, who's going to talk a little bit about, we talked earlier about some in situ and co-processing stuff, examples, and we'll let Venkat talk a little bit more about that.
So I'm Venkat Vishwanath. I'm a scientist at Argonne National Laboratory and work in different areas ranging from I/O, trying to do scalable analysis and system architectures, and how to design next generation systems too. So we have a very varied area of interest, and what we're seeing in future, or what we're seeing even currently, is that your compute capabilities is completely outweighing what your storage systems can do. So for example, when we went from ALCF1 to ALCF2, that's from Intrepid to Mira, we had close to a 20x improvement in our compute capability. If you look at our storage system from Intrepid to Mira, we increased by only 4. And you will see this trend as you go into future systems. So you have a much, the gap between the storage and your compute is going to widen. So one of the challenges that simulation sciences face at scale is I/O takes a lot of time. So we've worked with several application teams. For example, Flash, in some of their really large-scale runs, they spend 30% of their time doing I/O. And this is I/O for their checkpoints, restarts, analysis outputs. If you can actually reduce this, you can do a lot more science. You can have larger runs. You can do larger fidelity, larger scale science. So that's one of the big challenges that we are trying to overcome in large-scale simulations. So for example, Don Lamb at Flash calls storage the black hole, where you send your data and you never get time to analyze it. So what we are looking for, and several other groups throughout DOE and at other places, are how, instead of thinking about analysis and visualization as a post-processing tool where you write the data out to storage and then you visualize it, can you try and move some of these analysis and visualization right to where your simulation is taking place? So this is what we call simulation time analysis. And I'll be talking about some of the challenges in doing this at scale. So what you're seeing over here is the architecture of ALCF1. On the left is Intrepid, which is our BlueGene P system. This is connected over a network to both our analysis cluster, which is Eureka, as well as to our file system using a MirNet switch complex. This similar configuration is what you'll see on Mira 2. So you have Mira on the left, you have Tukey on the right, as well as the storage system. So you can actually send data from Mira to Tukey, in this case, Intrepid to Eureka, memory to memory, without having to go to the file system. So if you were to do simulation time analysis, you could either run some scalable analysis codes on the compute cores itself. You could move it to the I/O nodes. I'm sure they've explained to you the architecture, but for every 64 compute nodes, you have a dedicated I/O node. So you could move it over there, and you could perform some analysis on the I/O nodes. So your simulation is going ahead, and you can do your analysis concurrently on these I/O nodes. You could move it all the way to Eureka and perform your vision analysis. By moving it to Eureka, the advantage is you can fully exploit the large amount of memory that you have on Eureka. You can exploit the GPUs that are there. And again, you have these asynchronous capabilities that you can perform. There are opportunities to do it on the file system, file servers too. We have several examples where we have tried experiments on the file servers. This is a little bit more tough because it's a production file system. So, doing it either on the compute nodes, on the I/O nodes, or on Eureka these are more of the amenable architectural or infrastructure points where you can do your analysis and viz. So the question becomes, where do you do it? What's the right place and to do your analysis? And the answer is that you really need to take into account some of these system characteristics, what kind of analysis you're doing, to try and identify the right place to do it. So let me give you an example. Most simulation codes are very memory hungry or memory intensive. So for example, if you take HACC running on the Mira BlueGene Q system, it uses around 70 to 80% of its memory on its compute nodes. So if you were to do a temporal analysis where you needed multiple different time steps, you really don't have enough memory on these compute nodes where you can store these. So if you're doing very simple analysis where you're either trying to identify small features, simple statistics, where the analysis doesn't require too much of memory, or it can at least scale up. In some cases, analysis codes have always been designed for single nodes. You have very few of them that can scale up, so you have to design these new algorithms to scale these analysis tools. So taking into account these, you have to figure out where can you do it. So some simple analysis can be done in situ on the compute nodes itself. One big challenge over there is what happens if you're with the extra data set that your analysis is going to generate. So these are things that you have to work together with the applications to figure out where it can run in situ. What we have seen in practice is that you want to try and identify regions of interest on the compute cores itself, identify those regions, move them on to resources such as Eureka, and this is during simulation time, and then apply more fine-grained analysis, which are more time-consuming and compute-intensive on Eureka. So you have to try and balance this trade-off between moving data versus moving compute. So there is no single-shot solution. So if someone tells that in situ is the only way you can do it, you should try and ask these questions about memory consumption, what's the compute capability of these analysis algorithms. And I want to point out that post-processing is here to stay. There is a lot of exploratory analysis where you don't know where the data is being generated, but you don't know a priori what kind of analysis you want to apply to this data. Simulation time analysis, you basically need to know what you believe, what kind of analysis you can apply. But in many cases, you don't know a priori. So post-processing will always be there. And it's one of the big challenges that we have on how to architect storage systems to account for these. Any questions about these architectural features or points that we have? We've been working with a number of different application teams. Here is, we've been working with Ken Jansen at University of Colorado Boulder on trying to do simulation time analysis for the PASTA code. PASTA is an unstructured adaptive mesh that has scaled to 160,000 cores of blue gene P. It's scaled to 768,000 cores of blue gene Q. And we worked together with ParaView, taking data from PASTA using a framework that we've designed called Glean, and trying to couple ParaView running on Eureka, as you saw in the earlier case, with PASTA running on the compute nodes. So we were able to achieve close to a sustained data movement of 48 gigabytes per second. On Intrepid, the storage system can sustain close to, at production, around 10 to 15, given that the storage system is around 90% of its capacity. So you could easily get around a 4x improvement in the I/O capabilities there. But at the same time, you could start seeing features and trends. So here we are applying an isosurface as well as a cut plane at simulation time, live when it's going, when the simulation is evolving. So they found this really interesting, where they could see how is it evolving over a period of time, change some parameters, and run it again at scale. So you'll see more and more of such visualizations and infrastructures being adopted by scientists. So PASTA is one of the early adopters. There are several other, like you heard about LibSim, Catalyst. These are all infrastructure to enable such simulation time analysis. And definitely I think when you start using your codes, you should think about these tools that are available.